What does Mercury hide? Today, we set off to the most elusive of planets, a world blazing with light, cut by the silence of the void. Mercury, more than just a rock near the sun, an ancient mystery. From the earliest civilizations to modern probes, it eludes, it defies, it resists. What do we really know about this bright spot in the morning sky? And why, despite its small size, does it continue to fascinate humanity? But before embarking on a new adventure, don't forget to like the video and subscribe to the channel so you won't miss anything. Thank you and have a great journey. When we delve into the history of the observation of Mercury, one of the most discrete planets in the solar system, it is fascinating to trace back to the 14th century BCE. In those distant times, peoples were already looking up at the night sky, trying to unravel the mysteries of the movement of celestial bodies. One of these, often concealed by the solar light, gradually drew the attention of the first observers. Thus begins our journey into antiquity, discovering those early gazes cast upon Mercury. But how could one spot a planet so close to the sun? Ancient civilizations had to be ingenious to catch the rare glimmers of Mercury at dawn or dusk. The Babylonian tablets, called Mul-U-2 in their ancient transcription, are among the first documents clearly identifying Mercury as a body distinct from the sun. Written between the 14th century and the first millennium BCE, these texts formed rudimentary ephemerides, approximately indicating the dates and positions of visible celestial bodies. For the Babylonians, it was about figuring out when Mercury would appear on the horizon at either sunrise or sunset. The ability to predict these appearances confirmed the independent nature of this celestial object. In the Greek world of classical antiquity, Mercury was first named Stilbon, a word meaning bright or shining. Later, it was associated with Hermes, the messenger of the gods, known for his speed. This dual naming, born from confusion between the morning and evening stars, ended thanks to Pythagoras. Around the 6th century BCE, this thinker understood that it was one and the same celestial body, appearing at different times of the day. His discovery unified the Greek perception of Mercury. In China during the Zhou dynasty, astronomers developed an original method to calculate the synodic period of Mercury, the time needed for it to reappear in the same configuration relative to Earth and the Sun. Scholars precisely recorded the moments when Mercury aligned with the Sun, inscribing these events on long lists. They could then calculate the number of days separating two similar appearances of the planet and anticipate its future appearances. Here, conjunction referred to the moment when the body seemed to rise and set at the same time as the sun, or pass behind it. Chinese astronomers noted the date, the estimated time, and Mercury's position in the sky. This practice, called recording the conjunctions, allowed them to track the planet's cycles. Compared over the years, these observations highlighted a certain regularity, making it possible to establish more reliable calendars and a better understanding of celestial movements. These first steps in studying Mercury might suggest that the ancients had sophisticated techniques. However, the means of observation remained rudimentary. Without telescopes, the observers relied on their sight, sometimes aided by simple instruments like gnomons or bronze circles. These tools did not allow them to distinguish details of the planet. It was, for example, impossible to detect its phases or estimate its apparent size. Mercury appeared then as a mere luminous point, always close to the sun. Thus, observation was based on tracking its position relative to the day star. Ancient observers recorded the disappearances of the planet in the solar light, then its reappearances just before sunrise or just after sunset. This cycle, as brief as it was complex, reinforced the mystery surrounding Mercury. With each return, it seemed different, sometimes eluding predictions. Yet, the rigor and patience of the first astronomers laid the foundations of knowledge that continued to grow. Among the Babylonians, priest astronomers played a central role. They linked the movements of celestial bodies to signs intended to guide religious or political decisions. Mercury was observed with particular attention, used to plan rituals or advise rulers. This fusion between astrology and observation was not unique to Mesopotamia. The Greeks also saw Hermes as an intermediary between worlds, whose appearances influenced human destiny. In China, Mercury's conjunctions were integrated into calendar cycles, seen as markers of cosmic order. Despite these advances, the true nature of Mercury remained unclear. The ancients were unaware that it was an inner planet. They had no means of demonstrating that Mercury orbits closer to the Sun than Earth. They only noted that this celestial body never strayed far from the Sun's brilliance, as if it were bound to it. Precise measurements of its orbit, size, or distance were beyond reach. What remained was just an impression, that of a lively, elusive star, appearing briefly at dawn or dusk. These early observations, nonetheless, laid the groundwork for a rigorous exploration of Mercury. From the 14th century BCE until the 1st century CE, Babylonians, Greeks, and Chinese gradually refined their understanding of the sky. They identified Mercury as a distinct celestial body, named it, described it, and recorded its appearances. The technical limitations of the time, including the inability to distinguish fine details, did not hinder curiosity. On the contrary, it intensified, paving the way for great discoveries to come. During the period from the 2nd century AD to the 15th century, the study of the planet Mercury made significant progress in the context of medieval astronomy. Throughout these centuries, many scholars endeavored to describe the movement of this peculiar planet, difficult to observe because of its constant proximity to the Sun. The available instruments limited discoveries, but scholars from East and West made constant efforts to understand its trajectory and peculiarities. It is this thriving era that we will explore, by tracing the specific contributions of various thinkers and scholarly traditions. As early as the 2nd century, Claudius Ptolemy, a Greco-Egyptian astronomer, established himself as a major figure whose influence would endure for over a millennium. His fundamental work, the Almagest, advocates a geocentric conception of the universe, placing the Earth at the center around which all celestial bodies, including Mercury, revolve. To account for the irregularities observed in its trajectory, he developed a system of epicycles, a small circle traveled by the planet, itself carried on a larger circle. This complex geometric model aimed to reconcile observations with the mathematical knowledge of his time. Although puzzling to us, this construction was then an innovative approach to interpreting the available data, considering the technical limitations of the era. A fundamental aspect for explaining Mercury's behavior lies in the eccentricity of its orbit. The classic geocentric model assumes perfect circles, but accumulated observations show deviations that require adjustments. Between the 9th and 10th centuries, the Syrian astronomer al-Battani re-examined inherited data and proposed a correction of Mercury's orbital parameters. Eccentricity here refers to the deviation between the theoretical center of the orbital circle and the planet's actual position. Thanks to his highly precise records, Al-Battani published astronomical tables integrating these new values, which allowed for more accurate predictions of celestial movements. By refining calculations, the gaps between theory and reality diminished. In parallel, other civilizations developed their own approaches. In India, astronomers write the Surya Siddhanta, a major Sanskrit treatise on astronomy and mathematics. The text notably addresses the movement of Mercury and mentions transits in front of the Sun. Such a phenomenon occurs when the planet passes directly between the Earth and the solar star, appearing as a small dot on the bright disk. These transits, however, remain out of visual reach at the time since the solar glare masks the phenomenon. Indian astronomers then designed calculation methods to anticipate these invisible events. By relying on mathematical cycles and geometric models, they estimate the duration of Mercury's revolutions and seek to predict these passages. Although they cannot directly observe these transits, the rigor of their calculations already suggests the existence of a measurable order in celestial phenomena. In the Arab Islamic world, scholars developed treatises called ziji, compilations of astronomical tables and calculation methods intended to determine the position of celestial bodies. Written in Arabic, these works become the vector for the circulation of knowledge from various origins, enriched by Greek, Persian, and Indian traditions. Encouraged by the patronage of learned rulers, these scholars revisit the data transmitted by Ptolemy, especially regarding the inclination of Mercury's orbit. This parameter, which measures the angle between the planet's orbital plane and a celestial reference, is crucial for the accuracy of predictions. If poorly estimated, it renders the calculations incorrect and obscures the understanding of planetary motion. Therefore, it is a crucial element to master. Among these astronomers, Al-Zarqal, born in Al-Andalus in the 11th century, holds an important place. Known by his Latinized name Arzakel, he focuses on correcting the orbital values of the planets, including Mercury, through precise observations and rigorous calculations. He refines the measurements of inclination and takes interest in factors like precession, the slow rotation of the Earth's axis influencing long-term observations. Thanks to his work, astronomical tables become more reliable, allowing better anticipation of planetary positions. Throughout the Middle Ages, the transmission of knowledge relies on the translation of texts. Scholars of different faiths, based in intellectual centers like Baghdad, Toledo, or Cordoba, ensure the translation of Greek manuscripts into Arabic, and then from Arabic into Latin. These exchanges enrich the medieval Latin world, which gradually integrates the notions of epicycle, eccentricity, and inclination in its models. By the 13th century, European universities begin to appropriate this knowledge. Professors and students, often linked to the clergy, attempt to reconcile the astronomical concepts of Ptolemy with Aristotle's philosophy, despite the lack of technical tools to verify their hypotheses. Medieval astronomers face a significant challenge. Mercury's trajectory presents visible irregularities. Its appearance varies slightly at dawn and dusk, either ahead or behind schedule. To explain these shifts, the tables combine eccentricity adjustments, corrections of inclination, and precise positioning of the epicycle in the deferent. The geocentric model, although still dominant, begins to raise questions. To account for the complexity of Mercury's motion, additional elements are introduced, which complicate the structure of the system. Some go so far as to move the orbital foci, without challenging the Earth's centrality. It will take a later revolution to consider a new model, which is beyond our study period. This era leaves a considerable legacy in the study of Mercury. On one hand, it marks the emergence of an empirical method where models are continuously compared to observations. On the other hand, it illustrates the importance of collaboration across regions and cultures. Byzantine, Arab, Islamic, and Latin scholars dialogue through translations and travel. Mercury, called Hermes, Buddha, or Nabu, depending on the culture, fascinates researchers with its solar proximity and changing speed. It also holds a strong symbolic place in astrology, which reinforces the interest in its subject. From the 2nd to the 15th century, medieval astronomy laid the foundations for a deep understanding of Mercury, despite the absence of optical means capable of revealing its phases or diameter. Ptolemy introduced the concept of the interior epicycle, Al-Battani corrected the eccentricity, the Surya Siddhanta proposed calculations to anticipate transits, and the Arab Islamic astronomers integrated these contributions while improving the orbital inclination. Al-Zarqal stood out by refining the models in a critical and rigorous manner. On the eve of the Renaissance, these efforts gave birth to more complete astronomical tables, useful for court astrology as well as maritime navigation, even though Mercury remained less central than the Moon or Venus in this field. In seeking to understand this elusive planet, astronomers perfected their instruments and developed theories that would soon fuel debates around the geocentric model. In the year 1543, a major turning point occurred in the history of European astronomy. Nicholas Copernicus published a groundbreaking work devoted to the organization of the solar system. In it, he presented a radically new vision, placing the sun at the center and describing the planets as orbiting around it. To fully grasp the significance of this proposal, one must understand that until then, the Earth was considered the fixed point of the universe. The celestial bodies, including the sun, were believed to trace complex paths around our planet. By substituting the sun for the Earth in this central role, Copernicus sparked a total change of perspective. Celestial objects were no longer seen as mere points of light wandering on invisible spheres, but as distinct worlds, each following its own trajectory. This book not only challenged an ancient conception, but introduced a profound rupture that would take time to be accepted. Mercury, now placed closer to the sun than the Earth, became better understood. Its interior orbit explained the quickness of its movements around the central star. To explain what an interior orbit is, simple words suffice. An orbit is the path traveled by a planet around the sun. Saying that Mercury is interior means that it is situated between the Earth and the sun. If we list the planets starting from the star, Mercury comes first, followed by Venus, then Earth, and so on. In this organization, Mercury's proximity to the sun justifies its apparent speed in the sky, completing a full revolution in 88 Earth days, equivalent to 88 days. It speeds along at top speed, making it difficult to observe with the naked eye. The instruments of the time, still very rudimentary, did not allow for distinguishing its physical details. But the fact that it follows a shorter path than that of the Earth established an essential advance within the emerging heliocentric model. Addressing minds still unfamiliar with this new representation of the cosmos, this revision of Mercury's role becomes a powerful pedagogical tool. For centuries, Earth was considered the unique center around which everything revolved. Imagining that our planet is just one world among others radically disrupts long-held beliefs. Mercury's very close position relative to the Sun makes its observation even more challenging, which fueled the doubts of some contemporaries of Copernicus. However, over time, astronomers realized that its appearances and conjunctions were far more coherent in a Sun-centered model. Thus, Mercury became a key element in validating this new celestial architecture. Even without being able to distinguish its phases or measure its diameter, the calculations already allowed for understanding that this tiny planet follows a rapid and narrow path, hence its subtlety in the sky. A second pivotal moment occurred at the beginning of the 17th century, with the advent of highly precise astronomical calculations. Johannes Kepler, famous for his laws of planetary motion, set himself the mission of predicting celestial events. On May 7, 1631, according to his predictions, Mercury was to pass between the Earth and the Sun. This phenomenon, called a transit, refers to the moment when the planet is directly visible against the solar disk. Only Mercury and Venus can produce such a visual effect due to their position between us and the Sun. Today, these events are commonly anticipated thanks to tried and tested formulas, but at the time, without computational tools or powerful telescopes, Kepler's prediction was a true scientific feat. Relying solely on the distances and speeds from the heliocentric model, he calculated the angle under which the planet should appear and predicted the date of this fleeting passage. When the day came, a French astronomer and philosopher, Pierre Gassendi, decided to attempt the observation in Paris. He used a primitive telescope, a descendant of the first inventions meant to magnify the image of celestial bodies. The instrument remained imperfect, limited by its distortions and low power. Gassendi compensated for these weaknesses by projecting the image of the Sun onto a bright surface to spot the expected shadow. Against all odds, he managed to distinguish a small, dark spot moving across the bright disk. What he saw that day was a first in history, a planet visible crossing the face of the Sun. This success confirmed the accuracy of Kepler's calculations and provided striking evidence supporting the Copernican model. The trajectories aligned, the date was correct, and the observed size of Mercury matched expectations. The planet, with its 4,800 kilometers or 2,783 miles in diameter, appeared as a tiny black dot, validating the coherence of the prevailing theories. This observation was a major scientific breakthrough. It demonstrated that Mercury, as an inner planet, could pass in front of the Sun on precise dates. It also provided an educational example of the methods employed by astronomers like Kepler. One must calculate the orbital speed of the planet, its position in the sky, and predict the exact moment of its alignment with Earth and the Sun. This approach relies on the laws of celestial mechanics, developed through rigorous equations. Before this type of experimental validation, many scholars remained skeptical about the heliocentric model. However, when faced with the visual evidence of a transit, these reservations disappeared. The sky became a measurable space whose laws could be demonstrated through observation. At the same time, Galileo, an essential figure in modern astronomy, was also conducting research on Mercury with his telescope. He was interested in the phases, those changes in brightness, also observed on the Moon. This phenomenon results from the way the Sun illuminates a planet according to its position on the orbit. For the Moon, we refer to new, quarters, or full moon. For Mercury and Venus, it is a similar effect, proving that they orbit the Sun inside Earth's orbit. Enthusiastic about his discoveries on Venus, Galileo attempted to confirm the same observations on Mercury. However, its proximity to the Sun made the task difficult. His instrument did not allow him to clearly distinguish all the phases, leading to sometimes contradictory interpretations. Despite these limitations, his efforts testified to a growing interest in the detailed understanding of this elusive planet. During these early investigations, some scholars made interpretative errors. Simple spots on their lenses or on the solar disk were sometimes mistaken for transits. These confusions fueled controversies. In this context, Gassendi's successful observation in 1631 stood as an incontestable reference. It confirmed the reality of a fast and tiny object, as had been predicted by the calculations. The transit became a valuable tool. It allowed for verifying the positions of the planets, assessing the size of Mercury, and confirming its place in the solar order. These results significantly strengthened the Copernican model and attested to the precision of the laws developed by Kepler. Thus, the period from 1543 to 1639 represents a foundational stage in the study of Mercury. Copernicus, by proposing an inner orbit for this planet close to the Sun, provokes an intellectual shift. Kepler, with the finesse of his calculations, opens the way for unprecedented predictions. And Gassendi, through his meticulous observation, transforms a hypothesis into a tangible fact. Galileo's attempts, on the other hand, foreshadow future progress in understanding the illumination and movements of these worlds. Despite the initial hesitations, the study of the transit and the rigor of the demonstrations it allows to achieve will remain essential milestones. Step by step, scholars reveal the reality of a universe ordered around the Sun, where each planet follows its course according to precise laws. Mercury, first in the procession, continues to intrigue, defy observational instruments, and stimulate the curiosity of those who gaze at the sky. This chapter reminds us of how calculations, observation, and perseverance are the keys to any discovery. Between the mid-17th century and the end of the 18th, European astronomers multiplied their observations of Mercury, the planet closest to the Sun. Their instruments gradually gain in performance, lenses become more transparent, and telescopes more stable, making recordings more reliable. In this phase of exploration, the main challenge is to measure and refine the orbital parameters of Mercury to better understand its trajectory. The works of Giovanni Domenico Cassini, director of the Paris Observatory, play a major role in studying the planet's orbit and inclination. Until then, some fanciful theories suggested a halo of light around Mercury or abnormal movements. Cassini, recognized for the rigor of his planetary observations, directs his attention to Mercury with determination. Through several observation campaigns conducted in favorable conditions, he succeeds in measuring the inclination of the orbit with new precision. This angle, located between Mercury's orbital plane and that of Earth, is approximately 7 degrees, or 0.12 radians, according to his calculations. This data becomes essential for determining the moments when Mercury is visible near the Sun. Cassini's measurements allow the rejection of the idea of a luminous ring by revealing that some visual effects attributed to the planet were actually artifacts due to imperfect observation conditions. This clarification underscores the importance of improving instruments to distinguish Mercury's true characteristics. Some observers thought they perceived a halo when the planet was near the horizon. In reality, variations in the atmosphere and the deviation of light in contact with obstacles could create this illusion. Cassini manages to distinguish terrestrial origin phenomena from the actual properties of Mercury, consolidating the foundation of a more rigorous astronomy. At the same time, Edmund Halley focuses on the transits of Mercury, those moments when the planet passes in front of the solar disk. He proposes to precisely time these passages to evaluate the distance between Earth and the Sun, called the astronomical unit. By comparing the times recorded by astronomers on several continents, he hopes to calculate the scale of the solar system. This method requires extreme precision, reliable instruments, and international coordination. Mercury, fast on its inner orbit, offers several opportunities to observe these transits. Although more challenging to spot than Venus, it remains a valuable object of study for Halley. He calls for worldwide cooperation, urging astronomers to synchronize their efforts. This initiative embodies the new spirit of a science based on collaboration, standardization of methods, and confrontation of results. Meanwhile, another question fuels the debates, that of Mercury's rotation. Telescopes reveal dark spots on the surface, the nature of which remains enigmatic. Many astronomers then suppose that Mercury rotates on itself at the same speed. It completes a revolution around the Sun, constantly exposing the same hemisphere to the light. This idea could explain the apparent stability of its patterns, but the instruments are not yet advanced enough to confirm or refute this hypothesis. Some firmly support this theory, while others mention optical illusions or the limitations of telescopes. The conditions of observation, disturbed by the Earth's atmosphere and solar proximity, make analysis difficult. Despite all, the community agrees on a better understanding of the orbit. Cassini and his contemporaries refined astronomical tables, making period and inclination calculations more reliable in the service of navigation and mapping. In this context, some researchers imagine the extreme effects of a locked rotation. The side exposed to the sun could reach very high temperatures, while the other would be plunged into a freezing cold. However, no tool yet allows direct measurement of these values. Estimates rely on simple principles, such as the strong light concentration due to solar proximity and the absence of mechanisms capable of distributing heat. Astronomers also question the origin of the dark spots. Are they related to actual relief or illusions created by intense contrasts? The possibility of a light atmosphere is mentioned, but the dominant opinion remains that it is almost non-existent. In the absence of decisive evidence, hypotheses about Mercury's rotation and surface will fuel scientific curiosity for a long time. By the end of the 18th century, observation techniques improved, and orbital calculations gained accuracy. The quality of lenses improved, observatories became institutionalized, and surveys gained reliability. Yet, the solar glare continues to complicate the precise study of Mercury, visible only at dawn or twilight. The debate on rotation remains open, as no clear variation in surface patterns has been detected. The community nevertheless leans towards a slow rotation without being able to decide yet. At the end of this period, from 1640 to 1800, several certainties emerge. Mercury's orbit is inclined by about 7 degrees, or 4 degrees Fahrenheit, and does not have a bright ring. Transits become a central topic thanks to Halley's method to evaluate the Earth-Sun distance. As for rotation, it remains a mystery, which will still fuel discussions in the next century, when new instruments will rekindle the investigation. A decisive chapter remains to be written. In the mid-19th century, astronomers focused their attention on a peculiarity in Mercury's trajectory around the Sun. At first glance, this orbit seemed normal, but upon closer examination, an anomaly appeared. The point on the orbit, where Mercury is closest to the Sun, the perihelion, advanced slightly faster than calculations from celestial mechanics had predicted. The man who would highlight this difference was named Urbain Le Verrier, a French astronomer already famous for predicting the existence of Neptune from the irregularities in Uranus's motion. Around 1845, Le Verrier undertook a meticulous study of Mercury's orbital parameters to understand its subtleties. At that time, it was thought that all planets should flawlessly follow the gravitational laws established for 2 centuries. Yet, observations revealed a minute shift. To understand this anomaly, one must return to the notion of perihelion, the point closest to the Sun on a planet's elliptical trajectory. According to the laws in force, this point moves slightly over time under the influence of the attractions exerted by other bodies in the solar system. By taking all these influences into account, one could accurately calculate the expected movement of the perihelion. However, in the case of Mercury, this movement was faster than expected. Leverrier calculated that the observed speed of this movement exceeded the theoretical value by 43 seconds of arc per century. This figure, seemingly tiny, corresponded to an infinitesimal angular unit. But on an astronomical scale, it raised a fundamental question. Leverrier attempted to explain this mystery by hypothesizing that an unknown planet, located even closer to the Sun than Mercury, could be the source of this slight excess, an invisible mass whose gravity might have induced this additional motion. They named this hypothetical body Vulcan, in reference to a deity of heat and fire, imagining an incandescent body lurking in the immediate vicinity of the Sun. Astronomers then embarked on an ambitious quest to uncover this object by observing it directly. They initiated targeted campaigns under favorable conditions, particularly during total solar eclipses. At these times, the moon completely masks the solar disk, briefly plunging the sky into darkness sufficient to reveal potential objects near the Sun. During each eclipse, observers equipped with optical instruments scrutinized the solar corona, hoping to spot an unusual glow, different from a known star or planet. Stories circulated, with some claiming to have fleetingly seen a suspicious bright spot, perhaps Vulcan. But no observation provided decisive confirmation. The reports were uncertain, and the recorded positions varied from one eclipse to another. Caution was advisable. Many specialists pointed out that these fleeting visions could be optical effects or confusion with stars in the background. Gradually, the search for Vulcan became an exercise in scientific rigor. In the absence of irrefutable proof, every observation had to be validated with utmost precision. Astronomers multiplied the verifications, cross-referenced the data, and eliminated all sources of error: particles in the instruments, light effects, atmospheric turbulence, or misidentified stars. By the end of the century, despite numerous observation campaigns, no one had succeeded in establishing the existence of this body. Yet the idea did not disappear, for the anomaly in Mercury's movement remained, and no model managed to correct it within the established framework. Some astronomers then began considering other explanations. Perhaps the calculations of the forces exerted by the Sun needed refining, or previously unidentified physical phenomena had to be considered. Alternative hypotheses were advanced, such as the presence of an asteroid ring in an inner orbit. But these proposals failed to close the measured gap. In this context, a deeper question emerged. What if the theory itself was incomplete? For generations, scholars relied on Newton's laws to explain celestial movements. This framework had proven its worth repeatedly, notably during the discovery of Neptune. Yet, the example of Mercury showed a crack. People then wondered whether gravitation remained unchanged in all circumstances, or if it altered near a particularly intense field. Was it possible that the classical law ceased to be accurate at a very short distance from the sun? In this state of inquiry, a new perspective emerged. In 1915, a German physicist, Albert Einstein, proposed a radically different vision: general relativity. In this approach, gravitation was no longer a force in the usual sense, but the expression of space-time curvature. The sun, with its mass, distorted the spatial environment, forcing planets to follow curved trajectories. Applying this model to Mercury's case, the calculations provided a clear answer. The value of the perihelion advance matched exactly the 43 arcseconds observed, with no additional planet needed. This striking correspondence meant that with general relativity, Mercury's anomaly found a natural explanation. Invoking Vulcan became unnecessary to account for the planet's behavior. The new framework precisely predicted the evolution of the perihelion, thus offering a solution to a problem that had remained unanswered for over half a century. This success marked a historic milestone. For the first time, a new theory surpassed Newton's in a specific domain. The impact of this discovery was immense. Astronomers understood that the chapter begun by Leverrier was coming to an end. Vulcan did not exist. This realization strengthened the credibility of a revolutionary approach to space and time. Those who still doubted saw it as solid proof of the coherence of general relativity. The accuracy of the predictions, confirmed by observations, sparked international enthusiasm. Regarding the campaigns conducted during eclipses, they were not in vain. They allowed for the improvement of observation methods, better understanding of the limits of instruments, and highlighted the importance of data cross-referencing on a planetary scale. They also illustrated the caution necessary before announcing the discovery of a new celestial body, especially when the evidence is ambiguous or subject to interpretation. These lessons enriched the practice of astronomy, particularly in the search for bodies near the sun or still unknown. In 1915, when Einstein revealed that the mystery of the perihelion perfectly fit into his new theory, he put an end to decades of uncertainty. The idea of a blazing planet orbiting between Mercury and the Sun lost all scientific basis. In return, a deeper revelation emerged. Space itself curves under the influence of masses, and this deformation, invisible at our scales, becomes measurable where extreme conditions bring it forth. The case of Mercury illustrated this phenomenon. Vulcan then became a symbol, not of a planet, but of a milestone in scientific progress. This fascinating chapter extends from 1845 to 1915. From Leverrier's first intuition to the consecration of relativity, a whole generation of researchers mobilized to solve the enigma of the perihelion. Vulcan, conceived to fill a void, was never observed, despite extensive efforts. Einstein's theory definitively dismissed this hypothesis. What seemed to be a material gap became proof of a major conceptual advance. The quest for Vulcan, started as an empirical search, transformed into an intellectual revolution. Thus concludes this period between the discovery of an anomaly and the emergence of a new vision of the cosmos. It demonstrates how a tiny observation can lead to revising the foundations of a theory. It also shows that the caution of the scientific world, far from being a hindrance, ensures the solidity of knowledge. It took decades of efforts, debates, and doubts for a definitive explanation to arise. Vulcan did not exist, but its history illustrates the human passion for exploration, attention to detail, and the relentless will to understand what the sky does not readily reveal. And it is in this demanding quest that science patiently advances. Between 1962 and 1965, a major discovery disrupted our understanding of Mercury, the closest planet to the Sun. For centuries, it was believed that this small sphere, difficult to observe due to its proximity to the solar glare, always presented the same face to the day star. This idea, called day-year, was based on the hypothesis that its rotation duration exactly matched its orbital revolution. In other words, Mercury would make a full rotation on itself in 88 days, or 88 days, or the time it takes to orbit the Sun. This model seemed logical. It was thought that the solar gravity had locked the planet in a constant position, like the Moon continuously shows the same face to Earth. Yet this certainty was shaken by a series of innovative radar experiments conducted in the early 60s. To understand the scope of this discovery, one must focus on the method used by teams at the Goldstone Observatory in California and Arecibo in Puerto Rico. At that time, astronomers were exploring a new approach called bistatic radar. Unlike traditional methods, this technique relied on sending a signal from one site and receiving the echo on another. The goal was to combine the power of a transmitter with the sensitivity of a receiver. Specifically, researchers pointed an antenna toward Mercury, sent a radio pulse, and then analyzed the echo captured remotely. This process allowed for much better precision and provided the possibility to detect fine variations in the frequency and intensity of the reflected signals. The principle relied on the Doppler effect, which describes the frequency variation of a wave when there is relative movement between the emitter and the receiver. If Mercury truly had a rotation of 88 days or 88 days, the radar echo would have revealed a specific signature. But the data collected at Arecibo showed unexpected fluctuations incompatible with the day-year model. The analyses, led notably by Gordon Pettengill and Rolf Dice, revealed a faster rotation than expected, suggesting a more complex dynamic. Over time, the team calculated that Mercury rotates on its axis in about 58 days and a little more than half a day. This value, refined over time, was set at 58.646 days. This surprising data highlighted a 3-for-2 resonance. In 3 rotations, the planet completes 2 revolutions around the Sun. If you were on its surface, you would see the Sun traverse the sky very slowly, creating long days and unusual twilight transitions. The questioning of the day-year model shattered preconceived notions about Mercury. It was once believed to be static, with one scorching side and another frigid side. Instead, it was discovered to be a planet animated by a day-night cycle, with more nuanced thermal variations. With a rotation of 58 days, the temperature differences on the surface are staggering. Devoid of an atmosphere to moderate the extremes, Mercury can reach over 420 degrees Celsius, 708 degrees, under the Sun's glare, while at night, temperatures plunge below negative 170 degrees Celsius, 274 degrees. These violent contrasts directly influence the soil structure and the possibility of ice being present in certain sheltered areas. The slow rotation exposes each region to a long period of sunlight, followed by an extended frigid night. Scientists have studied the effect of these cycles on the rocky surface: expansion, contraction, cracks, erosion. These processes could alter some materials rich in minerals sensitive to heat. Without an atmosphere to protect them, the rocks also endure the impact of micrometeorites and solar winds. Another crucial point lies in the implications of this rotation on the potential presence of ice at the poles. In the 1960s, this idea seemed improbable, as the proximity to the sun appeared to exclude any conservation of water. But the rotation revealed by radar showed that some polar areas, never directly exposed to light, could remain perpetually in shadow. Crests or crater bottoms, plunged into darkness, would offer a natural refuge where ice could subsist. Subsequent observations confirmed this hypothesis with the detection of signatures compatible with frozen deposits in craters near the poles. Since then, the geological study of Mercury took a new turn. The fact that the planet alternates between light and darkness, rather than facing the sun permanently, reignited interest in its rocky formations. Experts wanted to know how the crust reacts to such prolonged thermal cycles. The faults and cliffs detected by subsequent missions like Mariner 10 or Messenger, could they result from internal contractions, or did the dynamics of rotation contribute to sculpting these features? Focusing on the planet's interior, researchers realized that the rotation also provided clues about its deep structure. Surprisingly dense, Mercury harbors a metallic core occupying a large part of its volume. A rotation of 58 days suggested that this core could be partially liquid, a condition favorable to the presence of a magnetic field. Although initial radar measurements did not target this phenomenon, they opened avenues regarding the planet's internal dynamics. If Mercury rotates faster than previously thought, it becomes relevant to wonder how its internal layers react to repeated gravitational tensions. The experiments at Goldstone and Arecibo sparked a scientific revival. Radar became a central tool for unraveling the mysteries of this unknown planet. Beyond rotation, it allowed the extraction of data on the surface, its texture, its topography, by observing the variations in the reflected signal intensity. These results were the prelude to what future space missions would explore in more detail. Among the most striking consequences of this discovery is the upheaval of the notion of a day on Mercury. From the ground, you would see the sun rise slowly after an interminable night, climb into the sky, and then give way again to darkness. This violent alternation imposes thermal constraints that slowly alter the planet's geology. For future exploratory vehicles, this knowledge of rotation was decisive. Planning a landing or a stay on Mercury implies precisely calculating the duration of the local day, the exposure to the sun, and the resistance of instruments to extreme temperatures. The duration of shadow, the available solar power, and thermal constraints become strategic elements. During the early 1970s, NASA launched an ambitious project to explore Mercury. The Mariner 10 mission, initiated in November 1973, became the first robotic spacecraft to approach the closest planet to the Sun. It used a gravitational assist from Venus, a technique still rare at the time, to accelerate its trajectory while saving fuel. This innovative approach reflects the ingenuity of the ground teams faced with the unique challenges posed by the inner planets of the solar system. On board Mariner 10, several scientific instruments were carried to analyze Mercury. An analog television camera, an ultraviolet spectrometer, and a magnetometer made up the main equipment. The camera served to map the surface during flybys, although its resolution was limited by the technology of the time. The ultraviolet spectrometer allowed the study of the tenuous exosphere, where rare gases appear under the influence of the solar wind. As for the magnetometer, it aimed to detect a potential internal magnetic field, a subject still uncertain before this historic journey. Mariner 10's first flyby of Mercury took place in February 1974 at about 700 kilometers or 435 miles altitude. The images transmitted surprised researchers. They revealed a surface riddled with craters of all sizes, sometimes clustered into vast impact basins. To their great surprise, relatively smooth plains were also visible, suggesting that ancient lava flows had shaped the landscape. This discovery challenged the idea that Mercury, too exposed to the sun, would have rapidly lost all geological activity. Another major revelation came from the detection of a global magnetic field. Thanks to the magnetometer, the team detected a faint but coherent signal, indicating the probable presence of a dynamic core beneath the surface. This finding disrupted established hypotheses, as it was thought that Mercury's small size would prevent any internal dynamo. Conversely, Mariner 10 suggested that a partially liquid core fuels this field, paving the way for new theories about the planet's internal structure. Researchers then considered a high metal content, explaining both its high density and the persistence of a magnetic field. During the second flyby, the probe continued its mapping by targeting other areas. The images revealed a remarkable diversity of reliefs, including overlapping craters, even larger plains, and giant cliffs called rupees. These formations, stretching hundreds of kilometers or miles, likely result from the planet's gradual contraction as it cooled, creating large escarpments. This observation supports the idea that Mercury experienced significant tectonic activity despite its small size and proximity to the Sun. Despite these advances, Mariner 10 never observed the entire planet. In all, it mapped only about 45% of the surface. The analog cameras showed their limits, with reduced sensitivity in certain lighting conditions. Thus, large areas remained in shadow or lacked clarity. The poles also escaped direct observation. Additionally, telemetry constraints complicated data transmission as the radio signal weakened as the probe moved away. Beyond the images, the mission delivered other valuable insights. Analyses suggested ancient volcanism, visible through vast uniform plains. Differences in albedo on the surface suggested varied mineral compositions, although black and white images made interpretation challenging. Observing the superimposed craters helped assess the relative age of the terrains, initiating a preliminary chronology of Mercury's formation. Scientists linked these structures to potential colossal impacts over time. The third flyby, in March 1975, allowed for the collection of some additional data before the end of the mission. However, the poles in other regions remained unobserved, while energy constraints limited operations. Despite this, Mariner 10 proved that a small planet close to the Sun could hide unsuspected internal activity. When contact was lost, nearly 2 years after launch, the probe left many puzzles behind, stimulating the desire for more complete future explorations. This historic mission painted a partial but striking portrait of Mercury. Less than half of the surface was observed, but the data revealed a complex world. Volcanic plains, fields of craters, and monumental cliffs testified to a rich geological evolution. Most notably, the discovery of a global magnetic field disrupted existing certainties. Without Mariner 10, these crucial clues would have remained in the shadows. The results sparked a keen interest in the scientific community, which then understood that Mercury might hold fundamental secrets about the genesis of terrestrial planets. It became urgent to send additional missions to uncover the remaining mysteries. Between 1976 and 2003, the study of the planet Mercury experienced what many astronomers called the golden age of ground-based radars and telemetric transits. During this period, several research teams around the world dedicated themselves to observing this little explored planet to uncover new mysteries related to its surface, composition, and orbit. The challenge was to better understand Mercury using tools different from conventional space missions, because since the previous flybys, notably those of Mariner 10, no new detailed images had enriched the available knowledge. Earth-based radars provided a unique opportunity to observe the planet closest to the Sun directly from our ground, while the transits allowed for coordinated observation of its passage in front of the Sun on an international scale. This phase marked a turning point in research, with astonishing discoveries and bold hypotheses, such as the possible presence of ice at the poles and fine analysis of its internal structure. To understand the contribution of these radar observations, one must first recall what a radar is and its interest in studying a celestial body as distant as this one. The term comes from English and designates a system based on the emission of radio waves toward a target, followed by the analysis of the echo returned. These waves can pass through the layers of the Earth's atmosphere or be reflected by the solid surfaces of distant objects. By studying the return signal, its frequency or intensity, researchers can deduce precise information about the speed, distance, structure, or composition of an object. For Mercury, the effectiveness of the radar depended notably on the power of emission and the size of the antenna used from Earth. Among the standout instruments of this period, the Arecibo radio telescope in Puerto Rico held a prominent place. Its immense antenna, carved into the ground, allowed for emitting and capturing waves with remarkable sensitivity. Between the late 1970s and early in the following decade, astronomers directed it towards Mercury in the hope of revealing its most astonishing secrets. That's how they detected echoes of surprising intensity originating from the polar regions. These so-called bright signals indicated that certain surfaces were reflecting the radio waves much more intensely than others. The polar areas, nestled in the depths of the caps, seemed to produce particularly clear signals. The explanation advanced at the time suggested the presence of water ice trapped in craters permanently shadowed. Despite the extreme temperatures that can exceed 400 degrees Celsius or 752 degrees Celsius on the sunlit surface, some polar regions, sheltered from direct light, maintain extremely low temperatures, sometimes less than 170 degrees Celsius or 274 degrees Celsius. These conditions could allow ice to persist, accumulated there by cometary deposits or internal processes. This hypothesis sent shockwaves through the scientific community as it challenged the image of a dried-up and burning world. Even in small quantities, the possible presence of water ice raised many questions. What was its extent? How could such a small planet, without a protective atmosphere, retain such deposits? What processes allowed their formation? From there, a wave of studies, theories, and models developed to try to solve this enigma. The data from Arecibo did not constitute definitive proof, but it was enough to spark keen interest and to launch new observation campaigns. Meanwhile, the study of Mercury's transits experienced a resurgence of interest, especially during the notable event of 1999, dubbed the Transit of the Millennium. This phenomenon occurs when a planet passes between an observer and the Sun, appearing as a dark spot moving slowly across the solar disk. For Mercury, these transits are relatively frequent, but they offer valuable opportunities to refine the knowledge of its orbit and apparent diameter. The 1999 transit brought together hundreds of astronomers, both amateur and professional, all mobilized to follow the movement of the planet in front of the sun and record synchronized data. Amateurs, equipped with solar telescopes and adapted filters, shared their results through online networks, while researchers used these observations to refine distance measurements, revise ephemerides, and confirm certain complex parameters of the orbit. This vast collective effort demonstrated the advantages of global coordination. Where once only a few facilities could conduct advanced observations, the end of the last century saw the development of communication means that favored networked work. The 1999 transit proved that the union of expertise, whether professional or amateur, could significantly advance scientific knowledge. Thanks to these shared observations, astronomers were able to confirm the regularity of Mercury's orbit and precisely determine its synodic period, which is the time needed for it to return to the same position relative to the Earth and the Sun. As observational campaigns intensified, theoretical research on Mercury continued, particularly around thermodynamic models related to the planet's internal composition. Mercury is known for its surprisingly high density, suggesting a very large metallic core. This core, primarily composed of iron, might contain a significant proportion of sulfide. This association between iron and sulfur interests scientists because it plays a role in the geological structure, internal behavior, and generation of a magnetic field. Thermodynamics, which studies the transfers of energy and heat mechanisms, helps understand how energy circulates within the core and how it can activate a dynamo, thereby generating a magnetic field through the internal movements of molten metal. Throughout this period, from the late 70s to the early 21st century, increasingly sophisticated models emerged to try to explain the high presence of iron, sulfur, and volatile elements at Mercury's core. Data from radar, particularly regarding surface reflectivity, were sometimes used to support these simulations. Researchers pondered, did Mercury form where it is today, or did it migrate from another part of the solar system? The proposed hypotheses suggested that the richness in iron and sulfur could result from a giant impact or a specific accretion phase at a time when the gas and dust disk originating the planets was still forming. These reflections have opened new perspectives on the origin of Mercury and its internal evolution. Results obtained thanks to ground-based radars, notably the one at Arecibo, have allowed for deeper research. Polar signals have revealed a planet far more complex than a simple dry and scorching rocky block, with the possible presence of ice reservoirs trapped in the shadow of its craters. The transit of the millennium in 1999 demonstrated the effectiveness of coordinated planetary scale observation. Thanks to precise measurements and global mobilization, researchers have strengthened ephemerides and refined orbital models, proving that even though Mercury seems inhospitable, it remains a planet full of surprises. Thus, over the years, researchers and enthusiasts have understood that Mercury was not just an inaccessible planet. It was also a true natural laboratory, capable of delivering precious clues about planetary formation. The Arecibo radio telescope revealed intriguing radar signatures, hinting at pockets of ice. The 1999 transit united a global community around the same goal. And while these data accumulated, specialists refined their internal models, placing iron sulfide at the heart of differentiation and heat transfer mechanisms. Even without new space missions at that time, this period marked a profound renewal of scientific interest in Mercury. In 2004, the Messenger mission was placed on the launch pad with an ambitious goal: to become the first probe to orbit the planet Mercury. At the time, this burning world, closest to the Sun, was still largely unknown. Previous flybys, like those of the Mariner 10 probe in the 1970s, had offered a first glimpse of its surface and environment. But researchers wanted to go further, to remain around the planet to study it continuously. This ambition was fueled by growing curiosity about Mercury's origin, composition, and evolution, with the hope of shedding light more broadly on the formation of the solar system. From the start, Messenger had to overcome a considerable technical challenge. Reaching Mercury from Earth did not simply mean racing toward the Sun. The probe had to be slowed down progressively to avoid being drawn into and precipitated toward the star. To achieve this, engineers designed a flight plan that included 6 planetary flybys to adjust its speed and trajectory while conserving fuel. By using the gravitational fields of Earth and Venus, Messenger gradually modified its orbit to plunge into the inner regions of the solar system and achieve the ideal configuration to reach Mercury. Between 2004 and 2011, the cruise phase was punctuated by crucial stages. The first flyby of Earth, 1 year after launch, allowed the testing of instruments and checking the probe's status. Then, 2 passes near Venus reduced its orbital speed and directed it toward Mercury's trajectory. Finally, 3 flybys of this planet in 2008 and 2009 provided a preview of the data to come and prepared the 2011 orbit insertion. At each pass, Messenger was already collecting images, exosphere analyses, and magnetic field readings. But it was the orbital entry in March 2011 that marked a decisive turning point. At this key moment, the probe stabilized around Mercury by combining the use of its thrusters and the planet's gravitational attraction. It then embarked on a campaign of close-up observations, producing a nearly complete map. These surveys unveiled a complex geology: volcanic plains, varied impact craters, and huge escarpments, indicating a slow contraction of the mantle and crust. The image of a dead and frozen planet quickly gave way to that of a world still shaped by internal processes. Among the major discoveries, Messenger identified high concentrations of volatile elements, such as potassium and sulfur, although they were expected to have vanished under extreme temperatures. These elements, normally prone to evaporation, appear to have been preserved or produced at different stages of Mercury's history, which complicates our understanding of its chemical evolution. Messenger also confirmed the probable presence of water ice in certain polar regions. While ground temperatures can exceed 400 degrees Celsius or 752 degrees Fahrenheit, areas permanently shaded at the bottom of deep craters remain cold enough to preserve the ice. The instruments of the probe detected signals compatible with these frozen deposits, later validated by analyses from NASA's JPL Center, which demonstrated that water could persist in these icy refuges, away from the sun's direct rays. By studying Mercury's internal structure, Messenger revealed that its core was not entirely solid. Gravitational and magnetic measurements showed that a significant part of this core remains molten. This observation challenges the notion that a small planet like Mercury would have completely solidified its core over time. The presence of liquid matter at its center suggests that a geodynamo is still active, explaining the existence of a global magnetic field, even if it is weak. Intriguingly, this magnetic field is offset to the north. the axis around which it is organized is not centered, suggesting internal peculiarities, perhaps related to an asymmetric distribution of heat or a novel configuration of the core. This anomaly could explain certain surface features, such as ancient volcanic areas or the appearance of the famous hollows, small depressions spotted on several planes. All these data gradually built a more nuanced image of Mercury. Before Messenger, it was imagined as a rocky block that had lost its light elements under the sun's influence. But evidence of preserved volatiles, past geological activity, and internal dynamics reveal a more vibrant world than it appears. Mercury, long considered an exception, ultimately shares certain traits with other inner planets. These revelations have also enriched our understanding of the solar system. By studying Mercury, scientists have explored new avenues to understand why rocky planets vary so much in composition. One hypothesis suggests that Mercury was born from iron-rich material, or that it underwent a giant collision that stripped away its outer layers. Messenger's measurements have allowed evaluation of the surface chemistry, traces of volcanism, and internal structure, thereby refining models of planetary formation. From 2011 to 2015, the orbital mission gathered an impressive volume of data. Thanks to instruments like the gamma-ray spectrometer, X-ray spectrometer, magnetometer, and laser altimeter, researchers were able to analyze terrain, distribution of elements, and the possible presence of ice. It was a patient effort, conducted in concert across multiple laboratories, with cross-validation between different devices. In 2015, the probe, nearing the end of its life, slowly approached the surface. Unable to maintain a stable orbit, it was deliberately directed toward a final impact. This act marked the end of the mission, but left an immense scientific legacy. The collected data are still being analyzed today, constituting the most comprehensive reference ever obtained on Mercury. Messenger's results have profoundly transformed our view of rocky planets. They now provide a basis for comparing Mercury to Venus, Earth, and Mars, as well as for considering the diversity of similar worlds around other stars. The chemical richness of the surface, the discovery of ice, the active magnetic field, and the complex internal structure offer numerous avenues of thought for planetary scientists and astrophysicists. In 11 years of travel and 4 years in orbit, Messenger has revolutionized our perception of Mercury. The 6 calculated and meticulously timed planetary flybys allowed access to a treasure trove of data. The data collected by the probe certified the unsuspected richness of this extreme world, revealing a planet far more active, complex, and intriguing than previously imagined. Thanks to Messenger, Mercury is no longer just a scorched rock orbiting the Sun. It is a major object of study whose singular history illuminates that of the entire solar system. When the Messenger probe crashed onto Mercury in 2015, researchers inherited an impressive corpus of data collected during 4 years of orbital observation. Between 2015 and 2017, the meticulous analysis of this information shed light on several key aspects of the planet closest to the Sun. Scientists particularly studied the strange configuration of the internal magnetic field, described as an asymmetric dynamo, and various rapid cooling scenarios. At the same time, increased attention was given to the presence of depressions, called hollows in English, and evidence of more recent explosive volcanism than previously thought. For the general public, it's worth recalling that Mercury, long perceived as almost inert, now reveals an unsuspected geological dynamism. MESSENGER, an acronym for Mercury surface, space environment, geochemistry, and ranging, allowed for the collection of high-resolution images, spectral measurements, and topographical surveys that highlighted a complex and structured crust. These observations formed the basis for new hypotheses, tested through demanding numerical simulations and precise comparative analyses. These are the results we will explore. One of the major contributions from this post-MESSENGER period lies in the study of Mercury's internal magnetic field. A planetary dynamo forms when the liquid core, mainly composed of molten iron, is stirred by rotation and temperature differences. This motion generates an electric current capable of producing a magnetic field. In Mercury's case, the readings indicate a clear shift towards the northern hemisphere, as if the internal motor were not perfectly centered. This particular configuration raises new questions about heat distribution and the circulation of molten material in the inner layers. Between 2015 and 2017, several computer models attempted to replicate this phenomenon. Researchers explored the possibility of uneven thermal gradients, potentially linked to Mercury's extreme proximity to the Sun. During the day, temperatures exceed 838 degrees Fahrenheit, or 470 degrees, while at night, they drop well below the freezing point. This extreme thermal contrast favors certain internal energy transfers that could influence the behavior of the core. Although still debated, these hypotheses today provide a solid theoretical framework for understanding Mercury's astonishing magnetic field shape. In the background, the new data gradually reinforces the validity of these scenarios. Another essential topic concerns the rapid cooling mechanisms that may have shaped Mercury's surface. According to studies conducted after the mission, Mercury would have lost its internal heat faster than expected, notably due to its thin crust and proximity to the Sun. Images sent by MESSENGER reveal the existence of spectacular faults, several hundreds of miles or kilometers long, which testify to planetary contraction linked to this cooling. Between 2015 and 2017, researchers refined estimates of density and thermal flux, confirming the idea of a core cooling significantly. This contraction manifests on the surface in the form of lobed escarpments, results of a slow geological process initiated hundreds of millions of years ago. Yet, the latest estimates suggest that the phenomenon may have continued much more recently, opening new perspectives on the planet's internal evolution. The models developed after the mission now take into account Mercury's high density to explain this accelerated heat dissipation, a central element for retracing the thermal history of this small, dense world. These advances lay the foundation for future observations and new experiments. In parallel, the identification of hollows has captivated the scientific community. These small depressions, with sharp contours and a lighter color than their immediate surroundings, were only observed thanks to MESSENGER. However, it wasn't until after 2015 that detection and spectral analysis methods truly improved. Researchers believe these hollows result from the sublimation of volatile compounds like sulfur or potassium trapped in the crust and released due to erosion caused by solar wind and thermal variations. Their formation is interpreted as an ongoing process, indicating a constantly evolving surface. Between 2015 and 2017, new topographic maps revealed an uneven distribution of these hollows, suggesting a heterogeneous composition based on the regions. Some areas show a high concentration, reinforcing the idea of an active geology. Their often fresher appearance compared to the surrounding terrain suggests that this phenomenon is recent or even ongoing. This discovery has opened up the possibility of an unexpected cycle of volatiles on Mercury, where the interior and surface interact in a fragile balance, subject to the extreme conditions of the solar environment. Finally, the question of explosive volcanism occurring more recently than previously thought was a significant topic in scientific discussions between 2015 and 2017. Until then, it was believed that Mercury's volcanic activity belonged to a very ancient past, but the analysis of pyroclastic deposits and related geological formations indicates more recent eruptions. The data shows regions where volcanic rocks appear less weathered, suggesting an age of a few 100 million years, relatively young on a planetary scale. The models are based on the idea that gases, trapped under pressure in the mantle, would have caused explosions when this pressure exceeded a critical threshold. Mercury's unusual composition, rich in iron and sulfur, could favor this type of activity. Between 2015 and 2017, several teams attempted to date these deposits precisely, revealing a more recent than expected volcanism, and potentially still active. These discoveries are shaking up the image of a static and arid planet and are redrawing the major lines of its geological evolution. They pave the way for new analyses and future exploration missions. In 2018, a new space adventure began for humanity, the launch of the BepiColombo mission. This name honors Giuseppe Colombo, an Italian mathematician and engineer whose work helped better understand how to use gravitational assistance to reach Mercury. This planet, the closest to the Sun, remains difficult to access due to intense solar attraction and the need to slow down sufficiently to enter orbit around it. BepiColombo embodies the challenge of placing 2 spacecraft around Mercury, each tasked with specific and complementary observations. The first orbiter, named the Mercury Planetary Orbiter, was developed by the European Space Agency. It is responsible for mapping Mercury's surface, studying its geology, and measuring its gravitational field. The second, built by the Japanese Space Agency, is called Mercury Magnetospheric Orbiter. It is dedicated to analyzing the magnetosphere, the zone dominated by the planet's magnetic field, in constant interaction with the solar wind. Studying this magnetosphere helps better understand Mercury's internal activity, particularly the existence of a liquid metal core, the source of a dynamo. This knowledge is essential for better understanding the fundamental mechanisms of planetary formation and evolution. To transport these 2 orbiters to Mercury, a structure capable of linking and propelling them over several years had to be designed, the transfer module. It functions as a tug thanks to electric propulsion or ion propulsion, a process in which a gas like xenon is ionized, then accelerated by an electric field. The ions thus projected create a weak but continuous thrust, very efficient over the long term. This technology saves fuel while reaching high speeds. The transfer module is equipped with several ion engines, powered by large solar panels deployed as soon as it enters Earth's orbit. BepiColombo's journey began on October 20, 2018, when a rocket took off from the Kourou base in French Guiana, carrying the entire device. A few minutes later, the probe was released into space, and the solar panels began to unfold to capture the light needed to power the instruments and propulsion. The probe first placed itself in an orbit around the Sun, similar to that of Earth, before starting a series of complex maneuvers to reach Mercury in a little over 7 years. A direct trajectory would have required too much fuel to counter the sun's gravitational pull. Engineers thus opted for another approach, gravitational assistance. By grazing certain planets, the probe uses their gravitational field to adjust its trajectory and gradually reduce its speed. For BepiColombo, this means a flyby of Earth, 2 flybys near Venus, and then 6 encounters with Mercury before the final orbital insertion. This plan, although long, optimizes fuel consumption, reduces constraints on propulsion, and allows scientific observations at each step. Between 2018 and 2021, the probe followed a spiraling trajectory around the Sun, gradually approaching its destination. This path could be compared to that of a cyclist choosing gentle slopes rather than a straight line to conserve energy. BepiColombo adopts this strategy. It takes calculated detours to maximize the benefit from the gravitational pull of the planets it passes. The first major step occurred on April 10, 2020, with a flyby of Earth. This passage allowed the probe's speed to be adjusted and prepared for its future rendezvous with Venus. The ground teams took the opportunity to test the onboard instruments. Even though Mercury remains the priority, these moments are valuable for checking the systems and obtaining useful data. The cameras captured stunning images of Earth and its environment, offering a glimpse of the ongoing journey. Two other key moments followed: the flybys of Venus in October 2020 and then in August 2021. At each passage, the speed and direction of the probe were recalibrated. These encounters also allowed data collection on Venus's upper atmosphere. Even though Mercury remains the target, each crossed planet offers scientific opportunities. The instruments measured the density of the upper layers and the infrared emissions of Venus. These data enrich those obtained from other missions to better understand the evolution of the Venusian climate. During this period, the preparation for the 6 flybys of Mercury remains the priority. With each passage near the planet, the probe decreases its relative speed a bit more thanks to Mercury's gravity. This gravitational braking is essential for a successful orbital insertion. The challenge is immense. Mercury is very close to the Sun and moves quickly. Each flyby requires keeping the probe in extreme thermal conditions. This is why BepiColombo has been equipped with thermal protections and radiators to dissipate heat. Between flybys, ion propulsion takes over. The electric engines operate for long periods to adjust the trajectory precisely. The thrust is weak, comparable to the weight of a sheet of paper, but constant. This regularity allows for a significant change in speed. Engineers monitor the xenon consumption and ensure the orientation of the solar panels. Each ignition is planned in coordination with the planetary flybys to adhere to the mission schedule. By the end of 2021, attention turns to the first flyby of Mercury, intended to give a taste of what awaits BepiColombo during its final insertion. Even without a stable orbit, the probe already begins collecting data on the planet's nearby environment. It detects charged particles and observes the exosphere, the very thin envelope around Mercury. The instruments, sometimes stored for protection, can then capture some opportune images of the surface. These first shots serve both as a control and scientific reconnaissance. In this context, international coordination is essential. Control centers in Europe and Japan exchange data daily to ensure the smooth progress of the journey. Communications with the probe, navigation maneuvers, instrument management, everything is synchronized. Antennas distributed across the planet allow us to receive signals from BepiColombo, check its status, and send new instructions. Scientists closely monitor each parameter, test algorithms, refine calibrations, and revise their hypotheses about Mercury. The 6 planned flybys of Mercury are the ultimate phase of this cruise. They help reduce the probe's orbital energy and initiate orbital insertion. This process, although long, ensures a controlled arrival. Once in position, BepiColombo will have the correct inclination and ideal speed to remain close to Mercury without depleting its fuel. The 2 orbiters will then detach from the transfer module to begin their scientific mission. This step will mark the start of a new chapter beyond the initial phase covered between 2018 and 2021. Thus, the BepiColombo mission embodies the ingenuity and patience necessary for planetary exploration. While the spacecraft continues its silent journey, its sensors prepare to examine Mercury in all its aspects. After years of flybys, precise calculations, and regular thrusts, a new era of discoveries will open up. Upcoming encounters with Mercury will finish slowing down the probe before its orbital insertion. That is when the in-depth study of the geology, chemistry, magnetosphere, and history of a discrete yet essential planet for understanding our solar system will begin. Since the very beginning of October 2021, the BepiColombo mission, jointly led by the European Space Agency and the Japan Aerospace Exploration Agency, has started to reveal unprecedented data about the planet Mercury during its very first flyby. This moment, often referred to as the first flyby, was a decisive step towards adjusting the trajectory of the orbiters to their final destination while collecting valuable initial information. The technical teams had meticulously planned this passage to capture high-resolution images and conduct targeted measurements. During this flyby, attention focused on the Debussy crater, a recent and remarkably well-preserved geological structure. The captured images revealed fine internal details, showing a succession of impacts at different periods. At the same time, researchers conducted a high-precision analysis of Mercury's exosphere, primarily composed of sodium. This study highlighted a great variability of gases under the influence of the intense solar wind. After a long cruise phase marked by trajectory adjustments and instrumental checks, the mission performed its third flyby of Mercury in 2023. Though numbered as the third, this encounter was actually the second scientific passage in close proximity to the planet, the second having been primarily devoted to navigation corrections. This key moment allowed the mapping of the electric currents present in the magnetotail, an extension of Mercury's magnetic field projected into space. The observations revealed significant reconfigurations of this magnetotail under the influence of particles coming from the sun. Plasma pulses can compress or stretch this structure, sometimes causing sudden magnetic reconnections. An article published in the journal Nature noted that the data obtained during this passage have deepened our understanding of energy exchanges between Mercury's upper atmosphere and the surrounding space, while providing new insights into the planet's interactions with solar eruptions. The fourth flyby, set for September 5, 2024, represented another major step in the study of Mercury's surface. The main objective was to capture detailed images of the Manly and Derain craters, 2 sites exhibiting fascinating geological features. Thanks to optimized cameras, the mission was able to identify terrace formations, well-defined ejecta, as well as fine variations in soil texture. These data could reveal signs of ancient volcanic activity or more recent geological transformations. The craters Manly and Durain are particularly intriguing due to their lighter hues, potentially linked to minerals containing volatile elements. On Mercury, where surface temperatures can exceed 400 degrees Celsius or 752 degrees Fahrenheit during the day, these elements easily dissipate. Yet images from the fourth flyby show localized deposits that might have been preserved beneath the surface or shielded by natural shadowed areas. This discovery raises new questions about local geological evolution. The fifth flyby, scheduled for December 1st, 2024, focused on thermal anomalies detected in Mercury's crust. Using a specialized infrared sensor, the mission highlighted areas of residual heat, which could indicate the existence of buried fossil magma chambers. By precisely analyzing these thermal emissions, scientists consider that ancient magma circulations might have remained active much longer than previously predicted by models. This suggests a more dynamic and recent volcanic past than expected. To delve deeper into this hypothesis, teams are examining the distribution of thermal fluxes and the chemical composition of rocks in the affected areas. These data could reveal a more pronounced internal differentiation, suggesting that the planet maintained prolonged internal activity after its formation. Such a perspective would challenge traditional scenarios, which posited that Mercury rapidly solidified due to cooling. Analyses continue with rigor. The sixth flyby, planned for January 9, 2025, will focus on exploring the night side of Mercury and the North Pole region. Due to the chosen trajectory, the probe will pass at an altitude of only 295 kilometers or 183 miles, allowing very close observations of the surface. In these low-light conditions, cameras will look for particular reflections related to the mineral properties of the soil. This extreme proximity will also facilitate the identification of tiny formations, previously invisible from a more distant orbit. Studying the hemisphere plunged in shadow offers a unique opportunity to probe craters where sunlight never penetrates. Researchers hope to detect ice pockets preserved in constantly cold areas, where temperatures drop well below 0 degrees Celsius or 32 degrees Fahrenheit. While some clues have already been noted, a low-altitude pass could confirm the presence of frozen deposits, paving the way for a better understanding of stable water presence on Mercury. Among the major objectives of this sixth flyby is also the detection of possible microwave auroras on the planet's dark side. On Earth, these luminous phenomena appear when solar particles interact with the upper atmosphere. On Mercury, with its weaker magnetic field and extremely thin atmosphere, the manifestations are different. BepiColombo's radio sensors will attempt to capture these subtle signals, potentially generated by collisions of energetic particles with the few gases still trapped around the planet. Between 2024 and 2025, new scientific advances have shed light on our understanding of Mercury. Long perceived as a simple rocky block with no apparent complexity, this small planet, the closest to the Sun, continues to surprise. Planetology labs worldwide have renewed interest in simulated samples and data from previous missions. In-depth analyses of its internal composition, combined with innovative numerical simulations, have led to the emergence of new hypotheses. One of them, suggesting the presence of a diamond layer at the boundary between the core and the mantle, is garnering growing attention. Initially proposed in restricted circles, this idea quickly gained traction in the scientific community, fueling debates and curiosity. To understand this hypothesis, one must turn to the extreme conditions at the heart of Mercury. Near the core, temperatures are said to rise to several thousand degrees, and the pressure would be gigantic. In such an environment, certain minerals adopt particularly dense crystalline structures like diamond derived from carbon. This phenomenon already exists on Earth, but in a more localized and modest fashion. However, there are indications that Mercury may have retained more original carbon inherited from its earliest moments. In the laboratory, these conditions are replicated using specialized presses, and initial results show that the transformation of carbon into diamond is conceivable. Such a layer would significantly alter the way the planet dissipates its heat, as diamond conducts heat better than silicate rocks. This could induce a novel mode of dissipation, influencing internal structure and material circulation. Meanwhile, expert teams in numerical simulation made a breakthrough in 2025. Thanks to increased computing power, they have developed sophisticated models tracing the early history of Mercury. According to these scenarios, the planet underwent a tangential impact during the formation of the solar system. Rather than a direct collision, a massive body would have struck it at an angle, stripping away a large part of its light mantle. This loss of volatile materials would have concentrated heavy elements and increased the proportion of iron. It is this configuration that would explain Mercury's high density, confirmed by the combined measurements of mass and radius. The study of impact features and global topography supports this idea, revealing a distribution compatible with such an ancient event. The models include parameters of oblique collision and compare them with available data, resulting in a remarkable agreement between theory and geological reality. During the same period, attention turned to the dynamics of sodium ions in Mercury's exosphere. This thin, gaseous layer surrounding the planet interacts strongly with the solar wind. To better understand these exchanges, specialists in magnetohydrodynamics have developed a two-fluid model. This model distinguishes between the solar plasma, ionized gas, and sodium ions that the solar wind continuously strips from the surface. The first results indicate that Mercury's magnetic field channels and redistributes these ions, creating local density variations around the planet like a moving veil. Published in an international journal, this work reveals a close link between the surface, the immediate space environment, and the sun's activity. These discoveries also fuel the reflection on Mercury's dynamo, a mechanism by which the internal movements of conductive fluids maintain a magnetic field. Mercury is the only terrestrial planet, along with Earth, to present a global field. For a long time, its small size and solar proximity seemed incompatible with such a process. But new thermal evolution calculations challenged this idea, suggesting the lasting presence of a partially liquid core. This core would still feed convection currents capable of maintaining the dynamo. Some studies show that residual heat is evacuated through chemical differentiation between the internal layers. Iron would gradually separate from other elements, like sulfur, causing persistent liquid movements. A diamond layer, if it exists, could speed up this thermal circulation and indirectly influence the intensity of the currents. Simulations now incorporate these elements, and the conclusion remains the same. An active, or at least partially functional dynamo is entirely plausible for several 100 million years. The internal heat, combined with Mercury's unique rotation, could thus suffice to sustain electric convection phenomena in the core. Even weakened by time, these movements would generate a measurable magnetic field. The variations observed over the years could not solely be explained by the influence of the solar wind, but indeed by an ongoing internal activity. This hypothesis sheds light on certain detected asymmetries, notably the displacement of the global field towards the north. More surprisingly, models suggest that even in the long term, Mercury could retain detectable magnetic signatures, albeit increasingly weaker as the heat depletes. That being said, this theoretical framework calls for further validation. Laboratories are constantly refining their protocols to accurately replicate Mercury's internal conditions. Numerical simulations are also advancing, incorporating an ever-increasing number of parameters. It remains to determine the exact amount of carbon that could form a diamond layer, as well as the precise angle of impact that would have given Mercury its density. The study of the exosphere's dynamics requires new observational benchmarks that will be provided by upcoming flybys and spectral analyses. As for the signs of a persistent dynamo, they give rise to great hopes. If the measurements confirm the presence of internal motion, we would then have a valuable clue about the thermal and magnetic evolution of rocky planets. All these discoveries, whether they involve a possible diamond layer, an ancient collision, the dynamics of sodium ions, or the resilience of the dynamo, have one thing in common. They reveal the complexity of a planet long underestimated. Despite its proximity to the Sun, Mercury now stands out as a key piece for understanding the chaotic youth of the solar system, the role of oblique impacts in planetary formation, and the limits of geophysics. Each advance raises new questions as exploration continues, and future missions promise to deepen the mystery. Thanks to future missions and laboratory advancements, current avenues will be refined, and new hypotheses will extend the investigation. In this crucial period extending from the year 2025 to 2026, the BepiColombo mission is preparing to enter a decisive phase, the insertion into Mercury's scientific orbit. This step marks the culmination of a long journey initiated several years earlier when teams designed the probe and defined its trajectory. Now, the objective is to precisely execute the final maneuvers that will allow BepiColombo to reach a stable orbit around the first planet of the solar system. Operations are expected to be completed around November 2026, after a series of flybys that will have gradually slowed the probe while adjusting its course. The choice of the orbital insertion date results from rigorous calculations on the speeds and directions to be adopted to counter the solar attraction, much more intense near Mercury than in more distant regions. The ground team continuously monitors the position of the spacecraft, relying on both ground antennas and onboard instruments that ensure navigation. The margin of error is tiny, as the slightest deviation could prevent capture or compromise the targeted orbit. Mission leaders anticipate a nominal duration of about 1 Earth year, with a possible extension depending on system conditions and available fuel reserves. One of the fundamental aspects of this phase is the mastery of electric propulsion, or ion propulsion, which BepiColombo uses to make gradual adjustments. Unlike chemical engines, which are more powerful but more fuel-consuming, this system uses ions accelerated by electric fields, allowing for fine speed management while saving fuel. Step by step, the probe will approach Mercury until it reaches the intended orbit to begin scientific observations. In parallel, during the year 2025, technical teams will also establish the roadmap for potential sample collection on Mercury. This project, still under study, poses a major challenge: how to extract rock or ice fragments from polar craters and then deliver them to Earth. These craters, located in areas where light never penetrates, might harbor preserved water ice. Their orientation and the absence of atmosphere keep certain areas in permanent shadow, with temperatures well below zero, 32 degrees Celsius, in stark contrast to sun-exposed regions where the heat can soar to several hundred degrees Celsius, over 572 degrees Celsius. To study the feasibility of this mission, an international working group coordinated by several space agencies is developing a document entitled Mercury Sample Return Roadmap. This plan lists the proposed technologies: solar sails utilizing light pressure for propulsion, chemical booster engines for landing and takeoff phases. The idea would be to deploy a lander equipped with drilling tools capable of collecting a few grams or ounces of soil or ice, before taking off again and joining an orbital module tasked with bringing the samples back to Earth. This bold scenario represents a long-standing goal for the scientific community. Directly obtaining materials from Mercury would deepen the understanding of planetary formation and evolution mechanisms. The analysis of mineral composition, the detection of volatile substances like sulfur, and the study of the internal structure of regolith grains. All these data could resolve certain uncertainties. Already, the Messenger mission had revealed hints of unexpected elements, suggesting an unsuspected geological complexity. Today, the hope of confirming these hints fuels the enthusiasm for a sample return mission. In this spirit of preparation, the BepiColombo team is also focusing on the deployment and calibration of scientific instruments that will come into action from the moment of orbital insertion. Among them are the Symbio-Swiss spectrometer, the MPO-MAG magnetometer, and a dust analyzer intended for the study of surrounding particles. The Symbio-Swiss spectrometer will observe Mercury's surface at various wavelengths to map the distribution of elements and reveal mineralogical contrasts. This approach will accurately depict the soil composition and shed light on the volcanic and tectonic history of the planet. The MPO-MAG magnetometer will investigate the internal magnetic field of Mercury, a topic that continues to intrigue researchers. The presence of a partially liquid metallic core would explain a relatively strong field for such a small planet. Yet, this field remains asymmetrical and seems shifted northward, a phenomenon that remains mysterious. The collected data will refine existing models and enhance understanding of the internal dynamics. Finally, the dust analyzer will play a crucial role in studying interactions between the surface and external particles, whether they come from the solar wind or micrometeorites. By measuring their composition, speed, and impact frequency, researchers will aim to evaluate erosion rates and the processes driving the evolution of the surface layer over time. The arrival of BepiColombo in orbit around Mercury, expected in November 2026, will mark the culmination of many years of preparation. Once the probe is stabilized, the instruments operational, and the scientific phase initiated, the first results can finally emerge, fueling the hope of a sample return mission from the planet closest to the Sun. By the horizon of the year 2027, a new era of exploration of the planet Mercury will begin with a series of ambitious projects aimed at deepening our understanding of this austere world. After decades of observations and space missions, the scientific community now relies on more sophisticated technologies and precision instruments. The objective is to take advantage of the latest advances in propulsion, data processing, and robotics to reveal subtle phenomena long out of reach. This period, stretching until 2040, will see the birth of new international partnerships and a strengthening of collaborations between industry and public research. At the heart of these future initiatives are proposals for small spacecraft called CubeSats. Designed to be compact and lightweight, these devices would accompany main missions by performing targeted tasks. Some might briefly land on Mercury's surface to install seismic sensors, while others would remain in orbit to monitor variations in the exosphere, the thin, gaseous envelope surrounding the planet. Thanks to their reduced size and technical capabilities, these satellites would pave the way for simultaneous observations at multiple sites, promoting a global understanding of Mercury's phenomena. To better understand the internal structure of Mercury, a network of seismic sensors distributed on the surface is planned. These instruments, sensitive to the smallest vibrations, would detect waves generated by earthquakes or micrometeorite impacts. By analyzing their propagation, planetary scientists could determine the composition and density of the planet's internal layers. This data would supplement knowledge gained from previous missions and could confirm the existence of a large core and a thin mantle. Meanwhile, ground-based observatories are preparing to utilize new telescopes with diameters of 30 meters or 98 feet, capable of scrutinizing Mercury with unprecedented resolution. Infrared imaging will reveal thermal contrasts on and below the surface, providing clues about material diversity, particularly mineral concentrations. This technology could identify areas where the crust is richer in iron sulfide, a key element in understanding the planet's internal chemistry. Located in regions where Earth's atmosphere is particularly stable, these telescopes will open a new window into Mercury's geology. Beyond instruments dedicated to Mercury, the next step involves enhanced cooperation with solar exploration programs such as the Helioswarm mission. Focused on studying the solar wind, this mission will provide data on the particle flux emitted by the Sun and its interaction with Mercury's magnetosphere. By comparing these results to measurements taken directly around the planet, researchers will better understand space erosion processes and the mechanisms of exosphere renewal. This connection between Mercury and the Sun represents a crucial research area for planetary physics. But beyond these technical feats, why focus on this scorching and discrete planet? Mercury, with its small size and high density, offers a unique setting to explore the early moments of solar system formation. Its atypical orbit and metal richness suggest a unique birth scenario, likely shaped by violent events. By tracing its evolution, scientists hope to glean lessons applicable to other rocky worlds and better understand the emergence of extreme planets in the universe. Thus, Mercury plays a central role in our cosmic quest. The unusual concentration of metals on Mercury, compared to other inner planets, raises questions about the distribution of heavy elements in the early disk. Some models suggest an intense thermal gradient associated with the action of the solar wind, favoring metal accumulation near the Sun. Others hypothesize a giant impact that stripped away much of the original crust, leaving an almost bare core. Understanding this metallic richness helps to better grasp planetary differentiation mechanisms and evaluate their scope in different stellar contexts. The study of Mercury thus sheds light on the primordial chemistry of our spatial neighborhood. Despite the extensive data already collected, some mysteries remain. The exact isotopic composition of Mercury, notably the distribution of its oxygen or magnesium isotopes, remains undetermined. These signatures reveal valuable information about the origin of the materials that formed the planet. The degassing processes responsible for feeding the exosphere are still poorly understood, and the question of polar ice continues to intrigue. How did these deposits form, and under what conditions do they persist so close to the Sun? New analysis methods could soon unveil these mysteries. High-resolution radars combined with spectral imaging could identify the precise nature of the ice hidden in the permanent shadow of polar craters. Thermal probes measuring temperatures at depth would help understand these ices' stability throughout the day-night cycle. These data would allow for monitoring their long-term evolution, suggesting the possible existence of preservation mechanisms, or, conversely, a slow erasure under solar radiation. These discoveries would guide upcoming robotic missions. The coming years promise spectacular advances in the exploration of Mercury. From 2027 to 2040, engineers and scientists will join forces to perfect propulsion techniques, send more agile probes, and refine data analysis. The first orbital insertions, expected as early as 2026, will mark the beginning of an intense scientific phase where each instrument will help unveil the secrets of this extreme planet. In the longer term, there are already plans for an autonomous seismic network, sample returns, and a gradual extension of our vision toward this fascinating world.